So I'll turn off my video for now and we'll concentrate on the introduction. So, hello everyone, and thank you very much for joining this tutorial. This is a continuation of our series of tutorials on the OpenPhase in OP Studio, dedicated to various aspects of simulations. For example, last time we actually concentrated on the coupling to the diffusion and simulating diffusion-controlled processes like solidification, for example. So this time we will concentrate on coupling to the elasticity, but also utilizing the knowledge from the previous tutorial. But those who weren't there, I will reiterate how we do that. How do we couple to diffusion as well? So in one simulation. So let me start with brief description of what's waiting for us today. So I'll start with a few announcements. Then I'll switch to OpenPhase tutorial on elasticity coupling, which will be presented on the example which is supplied with the academic version of OpenPhase, which is called Precipitation nickel titanium. So it's located in the example folder, and I'll show where it is. Next, I'll briefly present how to simulate the same situation or the same system using the OP Studio. So basically the same simulation setup, except that we will be using the Studio so that you have, the possibility to compare how easy it is or how much easier it is in the Studio than just tinkering with the OpenPhase itself. Adil Ali will present OPview, our new Python visualization tool, which will be available shortly. It's going to be open source and will be hosted on one of our web pages, and then we will end up with questions and answers. So let me first announce that, as mentioned before, now OpenPhase Academic version 2 is available on GitHub at the given address. So just go to github.com, icons, that's our institute, OpenPhase, and there you'll find the code. I'll show the web page later when we start with the tutorial, but in principle, that's where the source code is located, and you could grab it for yourself and try it at your own convenience. Next, our OpenPhase Solutions company got new web page look, so please visit, explore. There is significantly more information right now. There are solutions, product descriptions, other resources. Feel free to contact us if you have questions regarding the software and what we can offer. So the web page is available at openphase-solution.com. Next, I'll run directly into the tutorial. So brief introduction, why specifically this simulation example, and what is, particular about it. So we use the simulations for teaching already at our chair since more than 10 years. And this is one of the very illustrative and at the same time, easy simulation example on a system which has high technological relevance, and specifically precipitation, which could be used for tuning the properties of the material. For example, we know that nickel titanium shaped memory alloys are used almost everywhere in our everyday life. So from structural elements to medical applications, to antenna sensors, some wearables, for example, glasses or glass frames, in automotive for actuators and sensors. So this is just everywhere. But one of the peculiar aspects of the nickel titanium shaped memory alloy is depicted here on the left, is that martensite start temperature, that's actually the transition which is used in most applications, has very high sensitivity on the nickel content in the material. So for example, once you cross the 50% composition of nickel and titanium, then it abruptly, the martensite start temperature drops abruptly, and within 1.5% of nickel, it drops by 200 degrees, which is a lot. And so in order to catch a sweet spot or working point for your sensor, you actually have to hit an exact composition on this curve to tune your temperature, either it's room temperature or above room temperature. And that is, tricky procedure, especially in production, that actually explicitly hitting particular composition is not so easy, but precipitation of nickel 4 titanium 3 precipitates is a stoichiometric precipitates with slightly more nickel in them than titanium can be used to tune the final composition of your alloy, basically drifting along this curve as you need it. So you can prepare an alloy with slightly more nickel than necessary, and then by precipitating this stoichiometric precipitates, tune the composition and arrive at desired properties. And that actually is the interesting part. So knowing how these precipitates grow, the kinetics of growth, and knowing the nominal alloy composition, for example, like in this composition graph, scans through the particle here. So like as in the experiment, as you can see, these lenticular shaped particles in composition map of nickel depicted here. The nominal composition of the alloy was nearly 51% of nickel. And then after a while, when particles are growing, the composition in the alloy is dropping. And that's actually how it's tuned. And knowing how fast it does it will allow to control the process up until it basically arrives at the proper composition for your specific application. So why these precipitates are lenticular? So as you can see here, elongated shapes, is due to their particular symmetry. They are rhombohedral, so the unit cell is depicted here. So they're not cubic, so the matrix is BCC. It is a B2 structure of nickel and titanium. So where two cubic lattices are, how to say, put together, one containing nickel atoms and another one titanium atoms. But rhombohedral symmetry of the nickel 4 titanium 3 precipitates comes with the characteristic Eigenstrain or distortion of the lattice. So it actually slightly contracts in two direction and expands by almost 2% in the 1-1-1 direction. And since this is rhombohedral systems, there are 4 symmetry variants, and that's actually one of the other interesting aspects that we'll be also looking at. So we will also be looking at how to incorporate different symmetry variants into simulation. So by providing input for only one and actually providing an input how to generate the rest, all 4 symmetry variants. And that's actually, since we have 4 independent 1-1-1 directions, then we get 4 different orientations of the lenticular precipitates. We have also some knowledge of thermodynamics or hypothetic phase diagram, since these precipitates are metastable and never found as a bulk phase. So the phase diagram is constructed from known literature data. So, and that's what's used in the simulations. By this, I'm at the end of my introduction, and let me switch to the tutorial. So in order to start with tutorial, so you could get the code from the repository at GitHub, or you could just follow me, and then later on we can visit the page and I will show you around, or we can just start from it right now, since I'm sharing the screen. GitHub, items, OpenPhase. So here is the home of our repository. So it is part of our institute's repositories. There are other codes in there. And this is where you could get the code by just clicking this red button and then downloading the archive. Or you can clone it simply. So if you're familiar how the Git works. I already did that on my computer. So, and therefore I will start directly with the terminal. So I downloaded it into my home directory, and it is already in the folder OpenPhase main. That's exactly the name of the archive that you'll be getting from the GitHub. So if you list, so there are files and folders inside, which is much easier to view if we observe them in the file explorer. So in principle, the entire library is implemented in these 2 folders. So the includes and sources implementing the entire library. So for those who are not familiar with how the source codes are structured, so the headers contain declarations of all the functionality, and there is basically everything here: composition, boundary conditions, phase field down there. So phase field, and then also what's relevant for today, elastic properties and elasticity solver. So everything which we're going to use today is actually taken from this source code, and utilized. And everything is implemented, has the same structure, but now in CPP files inside of the repository. So let me switch to Eclipse, which provides significantly better view of the source code structure. So for example, the tutorial which we are going to follow today is located in the examples folder, precipitation nickel titanium. So you could later view it yourself in your own computers. If you open the CPP file, so we will see that it has some includes. Those who are familiar with CPP programming would recognize that we are including all the necessary functionality. So each module, actually, OpenPhase has modular structure, and each module is represented by its own header file. So we need diffusion, we need simulation settings, runtime control, interface properties, the double obstacle potential responsible for the phase field evolution, phase field itself, driving forces, composition, temperature. Initialization is used for simple initialization primitives. Then we include mechanics. Of course, we need boundary conditions and nucleation, and there is some, performance measuring tools, which is like time information. So you could monitor how your simulations perform. As you can see, we also have MPI parallelism is directly incorporated. So if you would compile with MPI parallelism enabled, so you will automatically be able to run the simulation in an MPI environment. Now we have to declare our objects. So everything we've included here. So we now use to create our objects. So we give them shorthand names. So phi for the phase field, double obstacle, elastic properties, elasticity solver, etc. So everything here is included, and that's where we start. So this is just declaring all the objects and feeding them the simulation settings. I'll show you when we go over the input what settings are and how it affects the simulation. Then we move to the initialization settings, so where we use one of the initialization where we just put a single phase, which is B2 matrix phase. It has index 0. So, and we give it orientation similar to the frame of reference. Orientation can be given, for example, here in Euler angles. So, and you can select convention of your convenience. So, and this is how we start. Then we have to set initial mole fractions in the system because it needs composition. We also have to set effective properties for elastic subsystem, and we solve once for mechanical equilibrium. And of course, we set the temperature. Also, the simulation can estimate its own time stepping based on the diffusion equation stability. For example, here is diffusion module knows diffusion coefficient and therefore can calculate for a given temperature what is a stable time stepping. That is used to run the simulation. And here we are entering into the time control loop. So this is basically where the actual simulation is done. This is about 100 lines long, but most of it is just some statistics gathering and output. So the actual simulation is performed in this part. So, and most of it is just timing statistics. You could just remove that, and then you will see that the actual simulation setup takes probably 20 code lines. So, but you don't have to start from scratch. You could just take one of the examples, either this or any of other available examples, and actually work your way through. So here, as you can see, we start with nucleation. So we need to nucleate seeds of precipitates, then we plant them, and then at some moment we will check the conditions whether they are met, and then either keep nuclei or remove nuclei. I'll stop on that a little later. Then we need interface properties. We also have to calculate phase field evolution due to capillarity forces. We once again have to update effective elastic properties based on the phase field evolution, because once phase field changes, we have to update the properties. We have to calculate driving forces, in this case, mechanical and also chemical. All is undefined here in these commands. So then after we have calculated the driving forces, we can check whether the nuclei have sufficient driving forces to survive, and therefore this check nuclei will decide which nuclei to keep. So then we update phase field by merging the driving forces into it, and then also we use elasticity solver to get elastic solution, elastic equilibrium solutions, and solve diffusion, etc. And then, of course, update the temperature. In this case, temperature is kept constant. Therefore, this function has to be called only once, but it doesn't harm once you switch to temperature change in simulation. Then we come to the output. There is a sequence. We write raw data for a start. So we write phase field, composition, and temperature. For a start, if you stop your simulation or if it's interrupted due to hardware software failure, you could pick up where you stopped, especially relevant for large simulations, and start from saving. And this is controlled by the frequency of output. So this is also an input which you could control. So then we write VTKs. VTKs are the visualization files used to visualize the microstructures using the VTK format. And for that, we use Paraview. I'll show you later how to use it and what you can get from it. So here we save a lot of data. We save phase fields themselves, which shows us the microstructure. We save composition. We save a bunch of mechanical properties for every grid cell in the simulation. So in this case, stresses, total strain, eigenstrains, effect elastic constants. We also write nucleation statistics, and we write driving forces in every point. And then, of course, we drop some statistics to screens that we know that our simulation is performing. And then, of course, we can print the whole clock summary of our performance. You will see all this once we start, but next, let's move to the project input. Project input used in this simulation. So whenever you see the read input functions, and they are also inside of the constructors of our objects, all these read input functions are reading this input file. And this one is simple ASCII file, just text. So, but it has sections. Every object, as you can see, runtime control field has its own section, starting with the add symbol. And there are settings in here, so starting with a $sign. So each setting has a short comment, and then after the colon has value. So in this case, we set up our simulation that we want to simulate for 10,000 time steps with 1 second. Where it is, sorry, with 1 second time step. So basically 10,000 seconds, and yeah, slightly less than 3 hours. Then we also specify how often we want to see the output to screen and how often we want to drop the output to disk, and then also restart output every 10,000 so that we don't have to save it right now because we don't expect an interruption. So this is how you control the runtime. So then you have to specify how big is your system has to be. So we know that precipitates are nanoscale, so they'll from tens to hundreds of nanometers, therefore our system has to be on the nanometer scale. So in this case, we select the resolution of about 4 nanometers, and then we specify the dimensions in 3 dimensions of 64 grid cells. Why this specific dimension, not 60, not 50, not 100? So these are powers of 2, which are very convenient for the elasticity solver, which runs significantly faster if it's powers of 2 dimensions because of the FFT algorithm. But any other dimension can work, so you're free to choose anything. And then this simulation will scale accordingly. With this grid resolution and this number of grid cells, we arrive at about 2.5 micron size. So we specify double resolution. This is an interesting feature introduced into the OpenPhase, where you could run phase field at 2 times higher resolution than any other field, allowing significantly faster simulation. So this really helps us to speed up on diffusion, because there we can coarsen the grid spacing and significantly speed up diffusion time stepping, and also keep resolution high at the same time. So, which means that phase field will have resolution of 128 grid cells, while all other fields, also elastic field, will have a resolution of 64 grid cells, minimizing the workload. Then we are starting to set up our system, where we come to the settings. And settings contain chemical composition of our systems are nickel and titanium, where we give names to all chemical components, all phases of B2, precipitate phase. Then we also specify the number of symmetry variants. For example, our cubic phase has single variant, while our precipitates have 4 variants, as depicted here. So we'll come to it later when it comes to setting up the symmetry variants, but before we'll go over some other settings. So driving forces are controlled by a driving force class. They're not only stored, they also average, so to smooth the phase field evolution, to avoid artifacts, etc. And instability of the interface. These values which you see are actually default values, and you may even omit them in your simulations, and they will be set automatically. So we use periodic boundary conditions in our simulation on all boundaries due to elasticity solver being periodic. And here we set up equilibrium partition diffusion. So we know that we set our reference element as being titanium. Then we specify the intersection of the solvers lines of both phases. Last time I already explained how the phase diagrams are constructed. So this is just like we specify the solvers of solidus and liquidus lines and their intersection points. So intersection is depicted by CSTS. This is where it's crossing in composition and temperature. Then we specify the slope of either line. So since our precipitates are stoichiometric, we cannot put here infinity, we just put 0, but the system will recognize it as infinity. So we specify diffusion coefficients. We also specify entropy of fusion from the thermodynamic data we know. So this is what is responsible for the chemical driving force. And then we, of course, indicate that our precipitates are stoichiometric, that the system knows how to handle them. So now we set the composition. So as you can see, we really follow name by name all the objects we have here. So each object has its own input, and then we specify initial composition in each phase. So in zeros phase and the first phase. So these are correspondingly B2 and equal for titanium 3. So we specify the initial composition in the matrix phase of 0.1% nickel, and complementary to titanium would be 1 minus this value. So we specify molar volume. We specify minimum and maximum range for the composition. It has been necessary earlier to stabilize better diffusion, but now these parameters are no longer necessary, and actually 0 and 1 interval for the composition is pretty safe everywhere. So this input is not actually necessary anymore. And now the tricky part, or the most interesting part, and this how to say sole purpose of today's tutorial, is the coupling to elasticity. So elastic properties contain significant number of input parameters and also the control or the boundary, mechanical boundary conditions. These are not the boundary conditions on the microstructure itself, but these are mechanical boundary conditions whether the system experiences any loads or it's free to expand, contract, and change its geometry. So these are just a list of possible mechanical boundary conditions. We can use implying strain rate. So if you have a sequence of loading increments, you also can use applied stress or free boundaries. Free boundaries is actually equivalent to applied stress of 0, so which means all boundaries are free to move until 0 stress condition is arrived. So the system is not under load. And this is what we set for all boundaries, but we will change it later once we come to it to illustrate. Then if you don't have free boundary conditions, but any of this, you could provide corresponding value for each boundary for X, Y, and Z phases, or also shear components X, Y, X, Z, and Y, Z. We can also specify the components if we have chemomechanical coupling enabled, and therefore we need these parameters if we have composition-dependent elastic properties, which we will not use in this simulation, but they are actually provided here in this input. So then we specify the elasticity model that we're going to use. We have several implemented. Kachaturen, and we have also rank 1, we have also Voigt and Royce, and we can specify a small strain framework for this simulation because strains are relatively small. Then we have input for the elasticity moduli, so C11, C12, and actually all non-zero moduli has to be input here. There are two possibilities, or actually there is a multitude of possibilities how to input elasticity moduli. Thanks to Raphael Schilling, who is here as well. We can input either elasticity modulus, Poisson ratio. We also can put Young's modulus, Lamé constant, bulk modulus, etc. Or we can go with full tensor or component-wise tensor entries. So choice is yours. Then we input the deformation or the stretch of the matrix, which is unit tensor. So the matrix doesn't want to stretch, it just stays as it is geometrically. So, and then we input the parameters for our precipitates. As you've seen, the precipitates are of rhombohedral symmetry, therefore elasticity tensor contains significantly more entries. And then we know already that the, how to say, precipitates deform tetragonally, so they actually compress significantly in one direction, but here we input these parameters in the natural basis of the precipitates themselves. And then we will later transform them into their actual orientation relative to the matrix. We don't engage in mechanical coupling, even though we could do just saying yes here, and here is the coupling parameters, and also thermomechanical coupling can be used if you have thermal expansion or thermal stiffening of material or softening. So we will not look into it, but if you wish, you could just engage it and provide necessary input. And here we are coming to symmetry variants. So since we know that our precipitates have 4 variants, so we start first providing variants for the matrix phase. So variant of phase 0 and variant 0. This is basically unit tensor, so nothing changes there. So the matrix doesn't change. While if you move to phase 1, so variant of phase 1, 0, 1, 2, 3, so 4 variants. These are transformation matrices which will automatically transform both the stretch and the stiffness tensor into the proper orientation relative to the matrix and produce 4 differently oriented precipitates families. Now nucleation allows the nucleation of precipitates inside of matrix. So phase 1 inside of phase 0, which is precipitates inside of matrix, we say yes, and provide parameters. So we can either provide the actual nucleation density, how many nuclei per given volume I expected, or we can provide directly number of sites, so or number of nuclei, skipping the calculations of the density. We can provide the nuclei size distribution. So in this case, we say normal distribution, center of the distribution, and deviation from the center are given here. We specify the range of temperatures where nucleation has to be attempted, so to avoid excessive attempts to nucleate where we don't expect nucleation, especially if it's outside of the stability range. So we also specify that precipitates have to their orientation from the parent grain. And we specify how many symmetry variants are allowed to nucleate per nucleation site, so just 1 in this case. And variant selection mode per site is random, so basically randomly distribute our precipitates and variants. Then we provide interface properties here, isotropic interface energy, very low in this case, and this is from some literature source, 0.035 joules per meter square, and the interface mobility of 5 to the 10 to the minus 18. Then temperature is kept constant. It's a typical annealing temperature of nickel titanium alloy used also in experiment. Typical annealing time would be about 10 hours. And the beauty of the simulation is that it actually runs in runtime. As we've seen at the beginning, the time step for this simulation is set to 1 second. And this is how it runs. So it runs with roughly 1 step per second, at least on my old laptop. So and if you go to bigger machine, higher parallel environments, then it will be much faster. So this is how the setup is working. So here you could also specify the number of open MP threads. You could just increase this number, save the setting, then go to the terminal. I already compiled the code, so but in principle you could just compile the library by typing make and hitting enter. In my case, it's quick because I already did that. So now only the Python bindings are being compiled, which is always happening. And after that, we'll switch to simulation itself. Okay, now we change to examples. Precipitation, nickel, titanium, we make there again. This is quick because our simulation code is pretty small, and then we can just engage. So we just type the name of executable, which is the same as the directory name and as the example name, and hit enter. What it does, it actually echo first to screen all the inputs we have provided. So it reads them all from the project input and put them out to screen. You also see that there are many default values which are not in the project input, but the system knows standard best values for various parameters, and that's actually what's used here. And you, of course, can experiment with these values after you learned a little bit about what they do. So after initial reading and setting up the simulation is done, then the nuclei are generated, as you remember, at the beginning of our simulation. We generate nuclei, and it will happen only once. Unless anything changes in the system, the new nuclei will be generated, but otherwise it is done once, and system monitors then later how the nuclei are planted and so on. Now we have the first output. So the system is basically 100% V2, as indicated here, and there is a tiny bit of nucleated precipitates. So this is just tiny seeds. We start with 0 volume seeds, and then they slowly grow and establish their own conditions and change composition, etc. And of course, here, as I mentioned, there is execution time statistics, so you could see how much time each of the modules is taken out of simulation time. Don't be confused by this discrepancy here. The file output is not included, and this one is really taking a long time. Now it's more realistic. So this is the, how long one time step takes to simulate on my laptop. It's 0.7 seconds, while the time step is actually 1 second. So we will finish the simulation soon as an experiment will finish in the lab. So this is just on this laptop. And then precipitates start to grow. Of course, we will not wait until the simulation completes because it will take maybe a couple of hours. But I already did this simulation before, and I have the data which I can show you. So if you go to Paraview, is a free tool. You could download it from the paraview.org webpage, or just Google Paraview and you'll find it. And then we can just go to previously simulated results. So first you start with wireframe, so empty box, and there is almost nothing in there. You can go to filters, ISO volume, select the phase fraction of, for example, phase 1, which is our precipitates, hit apply. At the beginning, there is nothing visible because precipitates are very tiny on the subgrid resolution, so you don't see them. Sorry, I have to move it out a little bit because I have the zoom control bar out there, which prevents me from clicking around. But if we advance, Paraview allows you to advance the entire sequence, we start to see precipitates appearing. At the beginning, they're very tiny, but you can already see that they have lenticular shape similar to what experiment does. And then in the color coding, we can select variants. And now you have 4 distinct colors, 0, 1, 2, 3, indicated by this variance color scale. These are exactly all 4 variants randomly generated that we set up. And as you can see, all of them are oriented perpendicular to a particular 1, 1, 1 direction of the initial B2 matrix phase. And this is how basically it happens in reality. Performing the simulation longer, so the precipitates grow until they exceed the chemical drain force and consume all the excess composition of nickel in the system. And then they will start to compete with each other for, the ripening will set in. But this one takes significantly longer times than just initial growth mode. Therefore, it is not simulated here, but just showing you how precipitation works and how elasticity, so instead of producing spherical particles here, elasticity really produces lenticular shaped particles just because it don't want to grow in the direction where it causes them the most of stress or elastic energy. So in the direction where they compress, where they want to be compressed by 3%. But they grow happily in the two other directions. In addition to the phase field and the microstructure itself, we can, of course, visualize other properties. We can visualize stresses. So much easier to visualize stresses on the surface. So we can disable the view of precipitates. We can monitor pressure, as you can see. Negative pressure inside of precipitates because they are under tension, and the positive pressure in the matrix. We can explore individual stress components. So shear components, basically everything in the system. We can also do line scans through the system. As you can see, there is an inspection line. You could specify direction in which it goes and start and end, and get a 2D view of our stresses in the system along this line. So you can specify all the components in this dialog here. So I will not spend much time on this, just to give you an impression of what you could examine in the simulation. So we could also visualize composition in the system. So we can disable the view of mechanics. We can monitor the total amount of nickel. As you can see, stoichiometric precipitates take 0.58 or up to 0.58. This is near the stoichiometry value, while the matrix remains around 50% of nickel. We can also inspect individual composition in each phase, or maybe, just let's take a line scan again through the system and monitor the composition of individual elements in different phases. You could see how the total composition is composed of the compositions of individual phases and how this overlaps in the interfaces here. So I will not spend much time on this for the sake of time, because we'll have to switch at some moment to the tutorial with the studio. But in the meantime, I would like to show you what can you do with the simulation to explore, for example, loading scenarios, and if you want to rotate your system, and how to do it. So I'll stop this simulation. We'll go to Eclipse, and here, instead of no rotation already prepared, we can orient 111 axis of our initial B2 phase along the 001 axis of the reference frame. So by that, to do that, we rotate pi over 4 around the x-axis backward, and then by roughly 1 radian, but in this case, it should be 0.95, but just to make it round, so by 1 radian back, and rerun the simulation. So after we've done such modification, we actually modified the source code of our executable, so we have to recompile it. And so then, and run it again. So if we run it, again, we will not wait until this particular simulation finish running. What we will do instead, we will open already saved simulation in rotated setting. We do the same filter, ISO volume. Again, phase fraction of our precipitates. And here, variance. As you can see, everything is turned now. So like, for example, if we split view and enable there the other view, oops, why isn't it working? Okay, so. So as you can see here, all the variants are oriented perpendicular to 1, 1, 1 axis. While here, one variant, this one, is oriented nearly perpendicular to the 00 to 1, 0 axis. That's actually was our intention. So slight misalignment just because we didn't use 0.95 radians, but just one. So which is a little bit an overshoot. So and this one variant compared to this structure, you see, is already rotated. So, and this is how you can change the orientation of your reference volume and simulate again, or how multi-grain simulations are performed. So different grains have different orientation, and it's automatically taken into account by rotating the entire structure inside. So, and then I also prepared the simulation with loading, but I think we already run out of time in this tutorial. So what you could do in the project input, instead of for example, instead of the boundary, you could just specify, for example, -1, I don't know, let's say -500 megapascal stress, and run the simulation again after you've saved it. And if you've done it, you would see slightly different structure. Now we are compressing in 1, 0 direction, so providing advantage for the red particle. So again, same procedure. Just disable. As you can see, all other particles are in disadvantage, while the red one is the biggest one of all. Here they are more or less uniform, but here, the red one, because it has the highest advantage, because we are compressing in the vertical direction, that's exactly what it wants, because it wants to shrink in that direction. So it has negative deformation in that direction, and therefore we are helping it by providing mechanical driving force advantage, and therefore it grows bigger than any other particle in this system. And then, of course, if you run the simulation longer, after the coarsening period, I think we'll have the only particle which is red in the system, and all others will vanish. And this is to illustrate what is possible when considering the coupling to elasticity. Of course, this is not the entire story. There is also possibility to couple to chemomechanical degrees of freedom, so where the coupling between chemistry and mechanics happens, the composition dependence of elasticity moduli, of transformation deformations, etc. Same with the temperature dependence, but this is just too much for a single session as we have today. So by this, I am at the end of OpenPhase academic tutorial. You could try this simulation by yourself on your own computers. It's pretty easy, as you can see. And in principle, in order to start with it, you don't even have to modify anything. Just open it, compile, run, and observe what it does. And once you are more or less familiar with how it does its stuff, then you can start changing parameters and actually performing numerical simulations or experimentation. So by this, I'll stop with the OpenPhase, and we'll switch to OP Studio. As you can see, as simulation progresses, the volume fraction of precipitates is growing, but it will take some time to get there. So we are now at 400 seconds in this particular simulation. In order to start with OP Studio, we will use the same example. I have it installed on my laptop. You can also request a demo and get it to try on your computers. So it starts with this dialog where you could start with a preset. If you don't have other simulations and you just want to try, it's exactly the same setting. It starts with a selection of chemical composition of your system. For example, select elements. They're already selected because we already set up this for you, but you could start from scratch and actually create a new project based on this interface. The interfaces B2, nickel for titanium 3. We also specify reference elements, say that they are solid. There is a choice liquid gas. If you have fluid dynamics coupling later. Once you set up your system, you can click next. And then you can gradually fill in all the properties for other objects. So all the objects which are marked here with solid squares, they are always included automatically because this is the absolute minimum for any simulation. Therefore, they're always in. And here we basically have the same input, the number of time steps, the name of the simulation, how often to output to disk, to screen. The time step in this case 4 seconds because it faster, similar to what we had in the simulation there. Specify number of OpenMP threads, for example, how often to restart, save for restarting, etc. And where to write the restart data, because also the studio monitors the restart data and actually it knows how many restarts have been saved. It has a little more functionalities than raw code that I just showed you. It has significantly more elaborate bookkeeping. So settings is empty because most of it has been done already on the first page where we specified phases and elements. Here we specify boundary conditions, which are periodic everywhere. So we also have drying force with all the averaging and so on. So grid parameters, interface width, grid spacing, similar, like number of grid cells in all directions, similar to the other simulation I just showed you. Here, resolution, we can select double for the phase field. Interface properties have similar structure, so we specify isotropic, but we also have cubic symmetry, stiffness model, hexagonal, a variety of hexagonal interface energies, models faceted, and also external means that you have to provide your own implementation. So you have plenty of choices and plenty of possibilities, also inputting the anisotropy parameters for all this. Also, you can have temperature-dependent interface mobility by providing activation energies, and then interface mobility will be temperature sensitive and will adapt itself as temperature changes. Temperature is the same, 773 kelvins. Here we use slightly different implementation of chemical diffusion and partitioning, which is multi-component in its essence, not only binary. Therefore, it has slightly different input. So we have plenty of control parameters here, so we can specify the diffusion model. We can also manipulate diffusivity metrics for multi-component if it's relevant, if some negative diffusivity components cause troubles, etc. We also specify initial system composition and also composition of individual phases. Basically, specify which phases is stoichiometric. There is also possibility to attach diffusion field extension to simulate bigger box than we actually simulate. Specify diffusion properties, they are located in the external input file. So we also specify for which phases to enable partitioning. Then we have kinetic interface where we use Arrhenius formula to calculate diffusivities, and the input is located in this OPID file, so where thermodynamics and kinetics is located. Similar for thermodynamic interface, also other properties So for the brevity, I will come closer to elasticity. So again, Khachaturian's model for elasticity, small strain, free boundaries, no loading on all axes. Tensor input, so you see full tensor, you can just fill in the coefficients. Same for precipitate. So input for the transformation-induced deformation, so no deformation for the matrix phase is unit tensor, and 3% contraction in that direction for the nickel for titanium 3 precipitates. Then we have elasticity solver. It has actually default parameters you don't have to worry about. They work pretty well for most cases, but here just to name, so that this stress accuracy is 100 kilopascal. This is where the solver will stop iterating, or 1 to the minus 6 strain conversions. And then we provide symmetry variants. So there you specify how many per phase and respective transformation matrices, similar to what we've done in the project input OPI file manually, but here you have more convenient input inside of the graphical user interface. Here's nucleation control. So you can specify where to nucleate so that we allow nucleation of nickel for titanium 3 particles inside of B2 matrix. We specify region, which is bulk, so everywhere. We specify the mode, density, or number of sites, in this case density, which we provide down here. So similar density as we had in the other file. So similar parameters to what we had before. So there are a few more control parameters you'll get familiar once you start working with them. As you can see, there is extensive help here of explaining what individual fields are. And yeah, this is it for simulation setup. Now you get to the microstructure setup. You specify initialization. You can add another initialization out of the list. So you can also start with Voronoi tessellation for polycrystal structures, for example, with randomly oriented grains. Or you start with a single one. So single phase, which is a B2 phase. In this case, you can select where to start, then apply and continue. Then basically, this is the simulation view. So you can save the simulation input. I already had this done before. And simulation starts. So here is the console output. So in a similar way as we had in the case of OpenPhase example, we have here statistics output, but also we have here output of simulation statistics. For example, if you want to see the volume fraction of nickel for titanium 3 precipitates, so we just enable it, and then if you wait a few outputs, then basically the curves start to appear. There is automatic update every other and then. And this is how you can monitor the simulation progress. At the same time, if you if you go to a dedicated simulation folder, I called it OP Studio Playground. So this is our simulation. Again, the same structure, VTK, and significantly more output there. We take phase fields. And we do again the same visualization. Again, take variants for color coding, and you see this is the same situation since the underneath we have the same library, same settings and everything. So then basically the microstructure is the same. There is no difference between the microstructure simulated with the studio and the one simulated with your base library out there. So an example provided there. So, but there is an advantage that you have graphical user interface and significantly tighter control of how you simulate and the settings, etc. So this is to give you an impression how the simulation work, how to visualize them, how to examine the data. And next, Adil will present our new OPview tool, which is a Python-based visualization tool to facilitate quick visualization of simulated results without the need to tinker with Paraview. because Paraview takes a little bit of learning to really get working. Here you can also stop simulation, go back, change settings, go back, start it again, and it will start with the new settings. Or you can you can save settings and move to high-performance computing facility and run your simulations there.